Hi everyone, welcome to all of you on my YouTube channel. I'm Ankit Mishra. I'm a GATE tutor for GATE Chemical Engineering. So I've been teaching from last 5 years on YouTube and with various another institute also. So here I am coming with the PYQ series of GATE previous year. So here you can see that I have already uploaded lots of previous year question papers solution on my YouTube channel. You can go, and I've completed the series of let's say process calculation, heterogeneous catalysis, non-ideal reactor, and again uh, I'm right now I have started with the mass transfer, and the first topic I'm going to start is distillation. So without wasting the time, let's start with the question first. So the question says that assume the is insoluble in water. The normal boiling point of benzene and water are 80.1 degrees centigrade and 100 degrees centigrade respectively. At a pressure of 1 atm, the boiling point of mixture of benzene and water is. So let's say if you see any questions that there is two mixture, let's say A and B, and both of these components are getting mixed and making a mixture of A plus B, and both of these are insoluble. So if it is insoluble, then both of these components will exert a partial pressure, individual partial pressure, let's say PA and PB, something like that. So PA set and PB set, that is vapor pressure. So when it comes to the boiling point of the mixture, since partial pressure exerted by both of these components will get added, and ultimately what will happen, it will reduce. So the boiling point of the mixture, here you will see boiling point of mixture will be less than the lowest boiling point, right? If it is insoluble. So if it is insoluble, then boiling point will be less than the lowest possible. So here you can see that boiling point is lowest one is 80.1 and highest one is 80. So it will be less than 80.1. But when it comes to the soluble, so the boiling point of mixture is, let's say Ta is less than Tab is less than Tb. So this is lowest boiling point, this one is the highest boiling point. So the boiling point of mixture will be in between the highest and lowest, right? So this one is the case that you have to understand when it is soluble and when it is insoluble. So in case of insoluble, it will be lower than the lowest one, and when it is soluble, then it will be in between. Next question is that for the nth tray column of the distillation column, if it is counted from bottom of a distillation column, the Murphy tray efficiency is given by. So when I talk about the Murphy tray efficiency, or Murphy plate efficiency, it is defined as the ratio of change in actual concentration to the change predicted by the equilibrium. So if I am talking about eta m, so I can write the formula change in actual concentration and divided by change in concentration predicted by equilibrium, right? So let's say if you have a plate, something like that, this one is the plate, and again if I say that this one is the nth plate, so the vapor which is coming to the nth plate, that will be coming from n plus 1 at plate, and the vapor which is going at nth plate, that is equals to, here that is yn, and here it mole fraction of liquid component which is coming is xn minus 1 and it is leaving is xn. Is that clear? So this is the actual thing that happens, and this is the actual nomenclature of the tray in distillation column. So when it comes to the plate end, so if I want to write ym Murphy efficiency here, so I can write obviously yn minus yn plus 1, that is change in concentration, yn minus yn plus 1, this is your yn plus 1, and divided by yn star, that is the equilibrium concentration, minus yn plus 1, right? So this is the fundamental thing, or when notation is from top to bottom. But here you are supposed to write the concentration or Murphy plate efficiency in terms of when this is just getting opposite. So here, if in this problem, let's say this one is nth stage and this one will be now n minus 1 at stage, and this one is your n plus 1 stage. So the vapor which is leaving from this plate is yn, and the vapor which is coming at this plate is yn minus 1. The liquid which is going is your x n plus 1, and which is leaving is your xn. So if I want to write y Murphy efficiency, then I can write yn minus 1 divided by yn star minus yn minus 1. Why? Because the notation now here is changed from bottom to top, not top to bottom, something like that. Okay, that's why this formula will be valid here. So now you can go and check your option, which option is following, which of the following option is correct. Yn minus 1 divided by yn star minus yn minus 1. So from here you can see your option B is correct answer. So this is very very important concept in case of distillation column, and very frequently they used to ask the question, or get used to ask the question from this particular concept. So you should know these things, how we can solve this kind of problem. Now coming to the next problem, that McCabe-Thally delta law states that the molar heat of vaporization of components are nearly equal. Linear crystal growth rate depends on the degree of supersaturation. Linear crystal growth rate does not depends upon the crystal size. Linear crystal growth rate depends upon the crystal size. So here directly you can visualize these things, that option B and C, B to D is not from the distillation, so only option A will be your correct. And again, in case of we assume that if a particular tray is there in the distillation column, so there happens equimolar counter diffusion. So if it is Na, then there will be Nb. So we know that Na, that is equals to minus Nb, and molar latent heat of vapor, I mean let's say the heat required for the vaporization of a more volatile component will be equals to heat lost by condensation of less volatile components. So if I want to write Na lambda A, that is equals to minus Nb lambda B. Why? Because this is going to lose heat, this is going to gain heat. Is that clear? And if I substitute Na equals to minus Nb, so I can write Na lambda A equals to Na lambda B. So Na will get cancelled out, so lambda A will be equals to lambda B. Means molar latent heat of vaporization of a component will be equal. So this is the fundamental concept of the McCabe-Thally diagram, and from here only this concept arises. Okay, so with that I'll move forward towards the next question of today's discussion. And the question says that according to the Fensky equation, what will be the minimum number of plate required in a distillation column to separate an equimolar binary mixture? So equimolar, when we talk about, so feed composition will be equals to 0.5. The mole fraction of more volatile component in the feed will be 0.5, and we to overheat fraction overhead fraction xd is given to you 0.99, and the bottom fraction contain 98% of B. So what is the mole fraction of A? So that is your 0.02. So this is B. I am assuming A is more volatile component, but bottom composition is given in terms of B, so you have to calculate in terms of A, right? That's why I have written in terms of that. And again, average relative volatility is given to you is 2, that does not change appreciably. Then you have to calculate number of these things. What will be the minimum number of plate required to you have to calculate the minimum number of plate required here. Okay, so let's try to solve. When we talk about if there is no reboiler and partial reboiler and condenser, so directly I can write formula like minimum number of plate, that is equals to log xd upon 1 minus xd multiplied with 1 minus xw upon xw and divided by log alpha average. So now I can substitute the value of all of these parameters that is given here. Xd is your 0.99 divided by 0.01 multiplied with 0.98 divided by 0.02. Sorry. Okay, so 1 minus xw is 0.98 divided by 0.02 and again divided by log of 2. Is that clear? So now this is up to you how you want to calculate. So directly you can calculate Nm will be equals to log 99 multiplied with 98 divided by 2 and divided by log 2. So once you calculate this question, sorry, once you will calculate these things, you will be getting, let's say I'll have to calculate these things then. 99 multiplied with 98 divided by 2, having log, and divided by log. So this is coming approximately 12. So your option C will be your correct answer. Is that clear? Okay, this is very fundamental equation. So you have to understand this, you have to remember this formula. This is called as a Fensky equation, and this will give you calculation of minimum number of stages required for distillation in the distillation column. Okay, so I'll be moving towards the next problem of today's discussion, and the question says that minimum reflux ratio in the distillation column results in. So when we talk about the minimum reflux ratio concept, so if you are talking about minimum reflux ratio, right? So just try to understand, if this one is a distillation column and here there is a condenser at the top and a reflux is taken back from the distillation column, so this reflux is coming back. So whenever if reflux you are increasing, then it requires a minimum number of trays, and if reflux is decreasing, then what will happen? If minimum reflux ratio is there, then definitely it will require less number of trays to do the distillation. But if you are increasing the reflux, then that requires the maximum number of trays or more number of trays for the distillation column. So let's say if you want to write the answer, then the option D will be your correct answer. That is the conceptual question. Now coming to the question 4.8, the question says that a distillation column separates 10,000 kilogram per hour of a benzene toluene mixture as shown in the figure below, and all of the mole fraction is given to you represented by these parameters, and you are supposed to calculate the reflux ratio, right? Okay, so whenever you want to calculate the reflux ratio is used to be equals to R is equals to L divided by D. So if you are able to calculate L and D, then definitely you are going to calculate the value of reflux ratio. So let's say if I will do the balance over here, I can write F is equals to D plus W, right? So I can write 10,000, that is equals to D plus W, that is equation first. And again if okay, so here you can see again I can also write 8,000, that is equals to L plus D. Is that clear? Okay, this is equation second, and again if I do the component balance, I can write F into XF, that is equals to D into XD plus W into XW, because composition is given. So F is your 10,000 multiplied with 0.5, that is equals to D, we don't know, 0.95, plus W also we don't know, 0.05. So we can calculate D from this particular equation. So that will be your 5,000, that is equals to 0.95 D plus W can be written as obviously 10,000 minus D multiplied with 0.05. That can be written as your, again, that is 5,000 so this is your 500, I think. Yeah, 500 minus 0.05 D, so that will be equals to 4500, that is equals to 0.90 D. So D can be written as 4500 multiplied with 100 divided by 90, so it will be, so your D will be equals to 5,000. So you have calculated D is 5,000. So what is L? L will be your 3,000, and what is R? R is equals to L divided by D, that is your 3 by 5, which is equals to 0.6. So you have calculated the reflux ratio is 0.6, right? This was also very fundamental question that requires the overall balance and component balance over the distillation column. That's it. Now moving towards the next question, the question says that The boiling point of a pure water and pure toluene are 100 and 106 degrees centigrade respectively. Toluene and water are completely immiscible in each other, well agitated. So here also the case is toluene and water are immiscible. So you have toluene, you have water, and you are going to mix it, and you are making a toluene plus water mixture, and this is insoluble in water, and boiling point of both of these components have been given to you, and the temperature at which the above mixture will exert a pressure of 1 standard atm is okay. So you are supposed to calculate the boiling point of this mixture. So I have told you when there is a case of insoluble component getting mixed to make a mixture, then the boiling point of this mixture will be less than the lowest one. So it will be less than 100 degrees centigrade, right? So less than 100 degrees centigrade. Next is at a total pressure of 1 standard atm exerted by the vapor of water and toluene, the mole fraction of xw in vapor phase satisfies. So just try to understand one thing here. As water has lower boiling point, that is 100, you can see, than the toluene at 1 atm pressure. So here what will happen? Pressure has a you can see that vapor phase will always be richer in water, right? Because if I'll boil this particular mixture, toluene plus water mixture, and if I am going to boil these things, so if it will be boiling, so first what will happen? Water will be there, water will start boiling because the boiling point is less. So mole fraction of water in vapor phase will be more, but can never be equal to 1, right? Why? Because some part of this toluene will be also going, right? Obviously mole fraction of water will be greater than mole fraction of toluene, but it is not going to be equals to 1. Is that clear? But always it will be richer in more volatile component, that is water. So you can assume that xw can never reach to 1, but xw will always be greater than 0.5, right? That will be richer in more volatile component. So if it is coming less than 0.5, so if it is coming less than 0.5, then there would be a case of that mole fraction of more volatile component will be less than 0.5. That can never happen. So here the mole fraction of water will be uh, 0.5 to 1. I hope this is clear to all of you. Okay, now I'll be moving towards the next problem, and the question says that in a distillation operation, what is the effect of the temperature of the reflux streaming on the condenser and the boiler load? So here if you see in the distillation column, something like that, so at the top you see there is condenser, and at the bottom you have a reboiler, something like that. So if reflux is completely liquid, so here if reflux is completely liquid, first case, and second case if reflux is below bubble point, if reflux is below bubble point, in that case what will happen? So if reflux is completely liquid, then there is no much more load on the condenser and the boiler. But if reflux is coming below the bubble point, then the load on the condenser and the boiler will get increased in second case compared to the first case. So your option D will be your correct answer. Okay, so with that I'd like to end this lecture, and in the next lecture I'll be starting with the next question that is also a theoretical question, and we'll see from there only. Okay, thank you. And if you have not shared my YouTube channel with your colleagues, please go and share with my channel, so that it will motivate me to make more videos from PYQ series and all of these things. Okay, thank you.